Okay. So we were saying that first I write three equations for this beam. From these three equations, I will get that by I can calculate it, ay I can calculate it, and I can say that ax is equal to bx, but still I cannot know their values, so I need additional equations. This is why I will pass to calculate for bc. I will put three equations for bc. Okay. Now for bc, I have uh, first I can write that sum of forces sum of forces along x equals to 0. This will give me that,
Doctor,
yeah,
excuse me, but did they ask us to get all the reactions and we must get CX CY?
yeah. Look, ما here's the idea. If you want to do a cut, always try to get the minimum number of reactions. Okay, so this is why you should read what they want from you. They want you to get the shear, normal, and moment at D and E. Okay, so if you want to do at D, you need AX AY. Did we found AX AY until now?
No.
No. So to calculate for D, you should find AX AY. And to calculate for E, if you want, no need to get CX CY. You can just get uh, for A, and you can just get AX and AY. But already to calculate AX AY, you will need to find CX CY in indirectly. Okay, so in this way, with E, it's easier to keep this part. This is why you should calculate both, يعني, if you want. Or another strategy is, for example, to let's say if you calculate bx by on bx by, okay, you can, when you do the cut here, you can take part bd, and when you do the cut at e, you can take part eb. So here you can just try to get bx by only, but when finding bx by, you might need to find other reactions. Okay, but if possible to get only bx
Yes.
by, don't do the remaining part. So let us see if this is
Yes.
possible. Okay, we can see first for by, you can do it by just doing what, sum of moments about a.
A.
Yes, so this is a good idea to not find all reactions. You can just do a small analysis at the beginning and say, how can I reduce my calculation? I can reduce my calculation if I just, when I do the cut, I will take only for part AB, I will take DB. So I need BX, BY. And for part E, to not have to calculate CX, CY, let us take part EB. It's also feasible. So you will say then, I'm not interested in AX, AY, CX, CY. I will try to get BX, BY without the other ones. So when you draw AB, you will say what equation will give me directly BY? It is sum of moments about A.
Moment about A.
Exactly. But for BX, I cannot get it directly. I need to look at the second part, which is BC. Okay. So now if I look at BC, I will try to find bx only without the need of getting cx, cy. Also, this is possible by doing what? So when you take part BC, a good idea will be to do sum of moments about C. Because when you do sum of moments about C, Cx, Cy will not be in the equation. And already By is calculated from the previous step. So what will be your only unknown then when you do sum of moments about C? Bx. Okay, so this is a strategy to reduce the calculation. So if they don't ask you in the problem calculate external forces, you can try to just get the external reaction just enough for you to perform your calculation for internal forces and moments. So no need, if possible, no need to calculate all reactions. You can reduce your calculations by proper selection, yani by saying that it's enough for me to know bx and by. This is why from the first beam, I will just get by. And once I get by from the first part, I will say that when considering member BC, in order to get bx, all I have to do is sum of moments about C. this will cancel moment of Cx, Cy, and already I know By, I can calculate Bx. Okay, so here to calculate Bx, what can we do? We can do just some of moments about
Sigma
C.
yes.
0. Yes, I will select a positive direction. I can take the counterclockwise as positive. So if I take the counterclockwise as positive, what do I have? I have first for Bx, it's a positive moment. So it's plus Bx times, what is the distance from C, the perpendicular distance? It's 1.5. So times 1.5. Now, for By is doing a clockwise moment about C, so it's minus. And the distance from C to By is 4 meters, so it's minus 4 By. Okay. Now I still have what? I still have the moment of the distributed load. And as we said, the distributed load is acting at 1 meter from B, or 0.5 meter from the base. So the distance between this force and C is equal to 0.5. And as you can see in the figure, it's producing a counterclockwise moment like Bx. So it's plus the value of this load. The value of this load is equal to the area of the triangle, okay, which is half 300 times 1.5. So it's 225. So it's plus 225 times the distance, which is 0.5, equals to 0. So already I know By. Since I know By, I replaced in the equation, I get now Bx. So as you said, no need to continue, because if I just do a smart choice, I can just limit myself to Bx, By. No need to calculate the other reactions. Okay, so now just I should pay attention that since I just calculated Bx, By, when I do the cut, I will take the part containing B. So here for part, when I do the cut at D, I will do the analysis of part BD. Okay, then on BD, what do I have? I have Bx, By, which are calculated. Okay, I have, and we assume they are like this. So this is Bx, this is By. Okay, and I have a force here. I can replace the distributed load here by one force equal to the resultant here of the distributed load. I have a rectangular part, so the force, the equivalent force, should pass by the middle of BD and is equal in magnitude to the area of this triangle. Sorry, this rectangle. This area is 2 times 250. So I have here 2 times 250 equals to 500. Okay. Now, in order to get the internal forces and moment at D, I will use my convention. Since I'm working on the left part, then I have my V is positive, sorry, my right part, BD. So V is positive upward, the normal reaction is positive towards the left, and the bending moment at D is positive clockwise to follow the conventions. So now all I have to do is to calculate the moment at D, the normal at D, and the shear at D. And to do this, so let me show you just the figure of BD alone, so it will be clearer for you. So this is the figure of BD segment. As you can see, you have the distributed load is equivalent to 500 Newton acting at the middle of BD. You have Bx, By already calculated from the previous step. And now to get ND, MD, and VD, I will write the 3 equations for this part. First, if I write sum of Fx equals to 0, I have a plus Bx minus ND equal to 0. This will give me the normal reaction at D. So ND is equal to Bx. Second step, sum of y equals to 0. What do I have along y? I have plus Vd minus 500 plus By, which is 500.
So it's 0.
So it's 0 exactly. Who can tell me why I can predict this result? Why I can predict that Vd is 0? Because look, this is a hint for you. Whenever I have a symmetrical load on a part, then V is 0 at the center. Okay? So here for this part, the load is symmetrical. Okay? So I will have V0 just at the middle. And we'll see this in detail. Yeah?
Which means whenever I cut in the middle, the V يعني upward or downward are 0.
Yes, exactly. So when you have a distributed load that is symmetrical with respect to your part, then at the middle of this part, so the shear should be equal to 0. Okay?
Yeah.
Okay. So here, then in the second step, okay, I have that, and here you have the symmetry is here if you want it to be here. And you have this part, okay, this part AB. AB is subjected to this rectangular part, okay. So here AB is undergoing a symmetrical load with respect to point D. Okay, this is why the shear at D, which is just at the middle of the beam, should be 0. Okay. Now, concerning so this is for the shear. Now for the bending moment MD, to get the value of MD, what should we do? Okay, to get the value of MD, we should say that
we can do moment about D.
Exactly.
Anyway,
moment about D equal to 0. When we do sum of moments about D, what do we have? We have first, let us take the, you can take the direction positive as you like. So you can take it clockwise or counterclockwise. Here I choose the counterclockwise as positive. So this is why I put in the equation minus MD, because MD is positive clockwise. So minus MD, you have also the moment of this force, okay, of the 500 Newton force. The moment of the 500 Newton force is clockwise, so it's also minus. So you have minus 500 times 1. But also you have another force doing a moment about D, which is the By force, okay? So the By force is doing a counterclockwise moment, so it's plus By times this distance, which is 2, okay? So you will get in this case that plus 500 times 2 equal to 0. This will give you minus MD plus 500 equal to 0, and you can get your moment at D. Okay, so in this way you can calculate normal shear and bending moment at point D. Okay, now second step is to calculate the values at E. Okay, so now also, as we said, because we know Bx, By, so I will work now on this part, this one. Okay, and I will say that this part should be in equilibrium. In this way, I can get the internal forces at point E. So this part is subjected to what? At B, we have the internal pin. So it's whenever I take the member BE itself, I have Bx, By at B. And I have the equivalent force here is equal to the area of the triangle and at a distance of 0.5 meters from E. So now all I have to do is to do the equilibrium relations on part BE. So now if I take part BE, this is the free body diagram of it, as you can see here. Okay, I have By, Bx already calculated. I have the equivalent of the triangular load, and I should calculate VE, ME, and NE. So here also, to get these three unknowns, I will write the three equilibrium equations. First, to get NE, I do sum of x equals 0. I have plus NE, minus NE minus Bx minus 225 equals to 0. So here it will be clear that NE should be in the opposite direction because it should oppose these two forces. So this is why you will get a negative result for NE. This means that your structure at E is undergoing compression. Now, concerning the shear value, I have plus VE, and as I told you before, always for shear convention. So here, this is the end of my beam. VE should be upward to rotate clockwise. So plus VE minus By equals to 0. So VE equals to By equals to 500. And finally, to get the value of the bending moment ME, I will do sum of moments about E equals to 0. I selected the counterclockwise as positive. So I have minus ME because ME is clockwise to compress the upper part of the beam. So plus ME, I have for the moment of the 225 Newton force, it's a counterclockwise moment, so it's positive, plus 225 times the distance to C, which is 0.5. And now for Bx, also it's a counterclockwise moment, so it's plus Bx times this distance, which is 1.5. And finally for By is rotating clockwise, so it's a negative moment, minus 500 times the distance from C to By, to the line of action of By, which is 2 meters. So this equation will give me the value of the bending moment at E. Okay? Any question on this? So as you can see, the internal forces are like a review for the equilibrium chapter. If you understand well the equilibrium chapter, it's just a small application. Just you should know how to do your cut. And once you do your cut, how to put the convention for shear, normal, and bending. And then you can deduce what will be the internal forces and moments. Okay?
Yes, doctor.
Okay. So we continue next time the problems, okay? Bye.
Okay, thank you.
Welcome.
Thank you, doctor.
Welcome.